There are two futures, the future of desire and the future of fate, and man's reason has never learned to separate them.
The Interplanetary Podcast, the exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Oh yeah, baby, Bernal.
Bernal. Papa Bernal, what's the score?
Well, I decided to make Papa Bernal the space legend of the month.
Well, I think it's fully deserved because the further we look into him, Matt, I mean, wow.
Oh my gosh.
OMG.
Oh my wow. We've got an interview with Fred Scharmen later on in this particular episode of the Interplanetary Podcast, Podcast 145.
And who is Fred Scharmen, Matthew?
Fred Scharmen is the Associate Professor of the Morgan State University. I believe he's an architect, but he's very, very interested in space architecture, as we'll hear. He's written some pretty amazing stuff, including a book that I'm reading at the moment called Space Settlements.
This is excellent news. We're going deep into this settlements in space thing, aren't we?
We're big time.
I mean, we're reading papers on trains. We're putting up photos on Instagram. I mean, how much more research do you want?
It's been a mind opener.
Has it?
One of the things that comes up quite a lot is the Bernal sphere, which as a space habitat. And that's because he mentioned this in a book. But just a quick background on John Desmond Bernal and really how space habitats sort of came out of the sort of social conscious of the time. There's something about the time of the 1920s and a little bit further on that made people start thinking about these things. But and Bernal's definitely falls in that category. But yeah, he was an Irish scientist. And he had really, really weird background of Jewish, Italian, Spanish, Portuguese, all sorts of things.
It's a good mix.
It's a good mix, but he's most famous for being a pioneer of X-ray crystallography, which at its time was the super cutting edge. This is how we learn what molecules actually look like.
It's weird because it's what I studied.
X-ray crystallography.
Yeah. I did X-ray crystallography and then art and design.
Jamie, are you confusing yourself with Rosalind Franklin?
Oh, yeah, sorry. Carry on.
Okay, so he went to Cambridge just to study maths and science.
Yeah.
Then the Royal Institute, where he did lots of work on graphite, including, almost sort of coming up with graphene, bizarrely. Then he went back to Cambridge. But because Ernest Rutherford, the great Ernest Rutherford, didn't like him, he didn't get tenure there, so he went to Birkbeck in London, where he was known as the Sage, because he was such a polymath, a scientist of dazzling intellectual ability.
I would love that nickname, even for a day. People to walk past me and go, all right, Sage.
It's a good herb as well.
It's a great herb.
Terrible accounts program. Ruined my life
Shout
for many years.
Shout out to all the accountants out there. Matt, I've got an accountant joke. Would you like it now or at the end?
I doubt we're going to bring up accountants again, so go for it.
What does an accountant do when they're constipated? Works it out with a pencil. What do you think? It's pretty good, isn't it? It's pretty good.
Yeah, I'm sure with a space thing we can somehow bring Uranus in there.
Oh dear.
What's very interesting about Bernal is that he never won a Nobel Prize, but lots of his students did. Dorothy Hodgkin, Max Perretz, Aaron Klug, they all won Nobel Prizes and they were all his students.
Wow.
So not only did he change the course of science, but he also was part of things. He was a witness and participant in things like the Easter Rebellion, the Great Strike, the anti-fascist movement, the pacifist cause, civil defence, RAF bombing strategy, planned the D-Day landings, was involved with post-war rebuilding, working on nuclear weapons.
Jeez.
Just a few things. he was he often found down at Downing Street or at the White House or at the Kremlin, where he was meeting Churchill, Stalin, Mao Zedong,
It's just where he knocked about.
Louis Mountbatten, Picasso, all the famous scientists of the 20th century. This guy was connected, like properly connected. But he's got quite a fruity private life as well. He was married to Agnes Eileen Sprague, who was a socialist, and they had an open marriage which they lived up to with great gusto.
Oh.
It says, yes.
Wow.
And so he had an affair with his genius student chemist Dorothy Hodgkin, who went on to win a Nobel Prize. He had long-term relationships with an artist, Margaret Gardner, and they had a couple of children. He had a couple of children with his wife, and he also had another child with Margot Heinemann. So, yeah.
Wow, what a cad.
So he was out there putting it about in both science and love.
And, so he wanted to also have children in space, I assume.
Yeah, he was an international man of mystery.
He was.
But why on earth are we talking about a biologist on the Interplanetary Podcast?
John, you're attempting re-entry.
The reason why he attempted re-entry several times was that he doing all this, he still had time to write lots and lots of science fiction books. Well, not science fiction books, but popular books on science and society.
You've got a favourite one, though, haven't you?
I have. And actually, it's pretty easy to find as a PDF online. And it's pretty quick read. It's called The World, the Flesh, and the Devil.
Wow.
Now, don't take my word for how good this book is, but Arthur C. Clarke describes it as the most brilliant attempt at scientific prediction ever made. Whereas Robert Skulls calls it a book of breathtaking scientific speculation that is probably the single most influential source of science fiction ideas.
Wow. That would do it.
So this is a short book that made those two people basically get quite hyperbolic about it all.
What is hyperbolic, Matt?
Look it up. Maybe we could have hyperbole.
I'm sorry, I know what
word.
it means. I was just being silly. I was just being really silly. I feel really silly today. Sorry, everyone. If you've got look, me and Matt are friends. If we were down the pub and he said hyperbolic, I'm going to say something silly. So I don't think I should be any different around you lot. There, I said it.
No, I agree.
So let's move on.
You set the tone for our Discord chatter as well.
Yeah, I heard that they're all potty mouths as well.
They certainly are. It's all about the world, the flesh, and the devil. And this is man's three struggles. And what basically he uses man's three struggles, the world, the flesh, and the devil, as a way of looking into the future. So the three kinds of struggles are the world, the massive, unintelligent forces of nature, heat, cold, wind, rivers, matter, energy, and all those kind of things.
Yeah.
That shape our destiny. Then the second, the flesh, things that are closer to us, things like animals and plants, our own bodies, health issues, disease. And then finally, the devil, our desires and our fears, our imaginations and stupidities. And all of these three things combine to sort of make us look into the future. And it's absolutely brilliant. It's clearly a brilliant mechanism for sort of working out how things are going to pan out, because as you'll see as I go through this, he comes up with some amazing kind of concepts and ideas that are just unbelievably close to the bone. It's amazing.
Wow. Okay.
So yes, he takes each of those divisions with the arbitrary assumption that that man's progress in it will continue, while on other aspects, man remains the same.
Ooh.
Oh, and I love this bit of the quote, is that the future being unknown and incontrovertible has been a fairground on which to place all our hopes and desires. But in scientific prediction, these desires are the most elusive guides. The opposite danger is, of course, a great and more insidious one. Of the present we take for granted to an extent far greater than we can realise. that all the developments that are going on will lead to a world incomparably more efficient and richer than the present. Bear in mind, this is 1929, capable of supporting a much larger population, secure from want and having ample leisure, but still a world limited in space to the surface of the globe and in time to the caprices of geological epochs. There in that one paragraph outlined why we should be building space settlements.
It's just genius.
Isn't that cool?
I mean, this is a long time ago too.
Yeah, 1929.
It's big things.
And then he says that we're already looking into conquering space, just as we've conquered the air. But even though this ambition seems fantastic, as time goes on, it will become reinforced by necessity. And then this is my favourite bit of the whole book. He meant this one sentence has been doing my head in. It may be that both the problem of space travel and the ethereal transference of energy have already been solved by Professor Japolsky's magnetofugal waves. I cannot find anywhere any reference to either of those two things, Professor Japolsky or magnetofugal waves. So if anyone out there knows what the hell that's about. I was going to
say, yeah, can you decode that, anyone?
Yeah, it'd be interesting that the fact that they thought, yes, that you could beam energy across, this was all about beaming energy, because he'd been talking about the rocket equation and how much you basically need all the fuel just to carry the fuel into space. And there had to be a better way of beaming energy to the spacecraft. Well, and that's why he mentions that.
Please get in touch, people. That's your homework for this week.
Yeah.
Please find that out. And I tell you what, Matt, if my nickname is going to be Sage, you can be Professor Japolsky. That is cool, isn't it?
I'm going to be called Professor Japolsky for the rest of the podcast.
Sage and Japolsky, that's like two kind of like kooky cops.
Oh, yes. Sage and Japolsky.
Sage and Japolsky. I've told you before, damn it.
Wanna fight about it?
You ripped up half of Manhattan. That kind of thing. Like we're being shouted at by the chief of police, Japolsky, put that away.
Getting back to point, Jamie. I know you're excitable this week.
I'm excited today. But it's because we're talking about space settlements. I mean, wow, this is exciting stuff.
So Bernal also pointed out that the first space vessels will be cramped and uncomfortable. And there'll be really problems landing on planets, so they'd have to probably come back with parachutes and all those sort of things. And this one's my favourite. If the problem of the utilisation of solar energy has by that time been solved, the movement of these space vessels can be maintained indefinitely, i.e. he's just predicted Voyager there. And, well, actually not Voyager, but any solar-powered spacecraft that's been going through the solar system. Actually, he doesn't mention nuclear power. So anyway, failing this, a form of space sailing might be developed by which the repulsive effect of the sun's rays instead of wind to increase its speed.
Hello, Planetary Society.
Yeah, as proved last week. 1929, he's talking about last week's success.
That is amazing.
Yeah, but this one is the bit that I think is the really great bit of insight. It says, so far, those who have considered spatial navigation have regarded it from the point of view of exploration and planetary visitation. But the vast importance of escaping from the Earth's gravitational field has been almost entirely overlooked. On Earth, even if we should use all the solar energy that we received, we should still be wasting all but 1/2 billionths of the energy that the sun gives out. And that, my friend, is the paragraph that goes on to inspire people like Dyson and the Dyson sphere, i.e. there's all this energy that the sun is pumping out. And we here on Earth, even if we were to capture all of that using solar panels, we'd only be catching 1/2 billionth of the energy.
God damn, that's insane.
When we get onto these space settlements like O'Neill cylinders and stuff like that, one of the things is that this absolutely abundance of space energy that from the sun, and that you could actually start a Dyson swarm of space habitats around the sun, and that's what made people from SETI, for example, look out for these swarms of space settlements that maybe advanced civilizations have. He then goes on to sort of talk about space fabrication, because then he says, getting things on and off the Earth is so difficult that if anything was damaged in space, you wouldn't be able to return, because a damaged space vessel almost certainly will be destroyed on re-entry. So he starts to talk about how the essentialness of building things out in space, a space infrastructure. This is 1929, and then he imagines, and this is the bit that people sort of go back to all the time, a spherical shell 10 miles or so in diameter, made of the lightest materials and mostly hollow. So, and he just thinks of it as a place where people can go and live. And the source of the material out of which would be in small part drawn from the Earth, for the great bulk of the structure would be made of the substance of one or more smaller asteroids, or the rings of Saturn, or planetary detritus. The initial stages of construction are the most difficult to imagine. They'll probably consist of attaching an asteroid of some 100 yards or so diameter to a space vessel. So he starts talking about all these things of going and grabbing asteroids and things like that. He's out there, man, doing pretty much a lot of the groundwork for what we're going to talk about.
What we're going to talk about is pretty much that. I mean, wow, hollowing it out and removing material to build the first protective shell.
Yeah. And
afterwards, the shell could be reworked bit by bit using elaborated and more suitable substances, and at the same time increasing its size by diminishing its thickness. Wow.
Yeah, and then he goes on to talk about the psychological aspects of people living in this Bernal sphere, and the criticism that habitants might be bored or
which we
find
talked
it
about
dull.
last week.
Yeah, and the diversity of the scene of animals and plants and all that. And then he sort of says, on the other hand, that there are people in his day that were quite scientists who are quite happy to spend all their time in the lab talking to their clever friends and things like that. So he kind of points out that humans are evolving already.
I don't want to be that guy, but if you think about social media these days, how much do people just spend hours a day just staring at their phone?
Exactly. So
you can't kind of go, oh, I'd really miss the plants. Would you? Am I getting too angry, Matt?
No, but I think that's a really important point, Jamie, that back in 1929, it must have been incredibly hard to perceive of humans being able to sort of cope with life indoors. Life just wasn't like that. But now that's kind of the life that we do lead. So, this was pretty forward-thinking stuff. Now, after reading this, I just thought, well, Bernal was just so ahead of his time. But then it's quite interesting when you look at the history, a really good look at the history of how space settlements kind of came together, and you can really start to see the ideas forming. So while Bernal's writing that book, Gerard Kitchen O'Neill. What a brilliant middle name that is, Kitchen.
Kitchen. Is that real?
Yeah. I think it's because it's his mum's surname, I think. But Kitchen, Gerard Kitchen O'Neill, was born 2 years before that book came out. So he's been born into this era of thinking. But there was an old man at the time, Konstantin Tsiolkovsky, that we talk about loads. And the reason why talk about him loads is because he simply is absolutely amazing. At that point, he's writing a book called The Will of the Universe, The Unknown Intelligence. And so in 1928, Jamie, he's writing about panpsychism that we brought up accidentally last podcast when I was talking about Sam Harris's wife's book, Anneka Harris's book. So
consciousness.
So panpsychism. I mean, it's just like, so Tsiolkovsky wrote about a whole load of things, but in 1903, he expanded on his description of man's space stations to include rotation for artificial gravity, the use of solar energy, greenhouses in space, closed ecological systems. And he would go on to state that he only came up with the Tsiolkovsky rocket equation as a kind of supplement to philosophical research on the subject. It's kind of like a side issue for him, the kind of maths and all that bit. He was much more interested in in paving the ways for humans to eventually colonize the Milky Way and beyond.
Wow.
But
it's just nuts.
Yeah, the first mention, as far as anyone can find, of a space settlement is called the Brick Moon.
1869.
Edward Everett. And basically, the Brick Moon is a story about these people accidentally sent into space in a brick building because it's catapulted into space, and they live happily on this brick moon. So it's obviously a bit silly and doesn't contain a lot of the details. But Jules Verne and Kurd Latzwitz all wrote about space habitats from that point onwards, some 1878, 1897. But this one is incredible. 1918, Robert Goddard, the famous Goddard, who essentially invented liquid rockets, he wrote about a nuclear-propelled space ark carrying civilizations from a dying solar system towards another star for a new beginning. So he came up with that concept. But get this, he kept it secret in a sealed envelope for over 50 years for fear of professional humiliation.
Oh, that's sad.
Yeah, so no one heard about his genius idea. But in the 1920s, a couple of years later, Goddard then suggested the use of extraterrestrial resources to manufacture propellants and structure. So this is a little bit before Bernal's book. So Goddard's already seeing the sense of using in-space resources. And then in pops another giant of space, Obert, in 1923. Hermann Obert elaborated on the potential use of space stations and noted that they could be used as platforms for scientific research, astronomical observations, and Earthwatch. So essentially describes the International Space Station. 1928, Guido von Dacke. He considers 3 stations, one low, one high, and one that's elliptical orbit going in between them and servicing them. So thinking of refueling depots for deep space flights. And then Potočnik, who was writing as a guy called Hermann Nordung, came up with the concept of a rotating wheel-shaped space station called the Wernrad, or living wheel. And it would be in geostationary orbit. Robert A. Heinlein expanded the interstellar arc concept of Goddard, although I don't know whether he would have known about Goddard's work. H.E. Ross from the British Interplanetary Society, the guy that designed that spacesuit that you often see. In 1949, he came up with the concept of a geosynchronous rotating boom, which takes out all the mass element of it. So you've got basically 2 things either side, and you create artificial gravity that way. Werner von Braun takes the Nording wheel and makes it pretty famous in those kind of Disney films that we see of von Braun's space station. 1952, he starts suggesting a 76-meter diameter at a 1,730-kilometer orbit. And in the same year, Arthur C. Clarke is writing his novel Islands in the Sky about even larger stations. And L.R. Shepard is envisaging a nuclear-powered million-ton interstellar colony vehicle called Noah's Ark.
Interesting.
1961, Arthur C. Clarke again starts suggesting that we should be putting large space stations in the Lagrange points.
Oh, that guy.
Yeah, so they can sort of stay fixed in one point. Oh, Jamie, I tell you what came up in the Discord. ZZ Top, a song that needs to go into the Spotify playlist. They've written a song about Lagrange points.
No way. How did we miss that?
I know. So it's got to go in.
Get in there.
Yeah, get in, ZZ Top.
Thank you, Discord.
1956, Darrell Romick proposed the cylinder, 1 kilometre long, 300 metres in diameter, rotating that 20,000 people could live in. So that's 1956. So we've moved on from the time of Bernal now. 1963, Dandridge Cole suggested hollowing out asteroids. So that's a pretty huge one, because we'll talk about that either this week or next week. And then, of course, 1969 sees the moon landing. But Gerard Kitchen O'Neill also in 1969 asks his students whether they to start designing large structures in outer space and what they should look like. And they do a lot of work on this. And he started putting together a paper called The Colonization of Space. And it's worth actually thinking of O'Neill. He was a very, very clever guy. He was rejected as an astronaut candidate, but did quite a lot of the training to become an astronaut. So that would have been interesting. But he invented the particle storage ring, which is a really important part of particle accelerators. So it keeps the particles whizzing around in a kind of storage ring before you fire them off. So he was heavily involved in sort of high particle physics, high energy particle physics. And he also invented, although I'm not sure he did invent, but he was very, very important in the development of the mass driver, which is those rail guns where you fire mass off the moon, for example. But Arthur C. Clarke also came up with that concept. It's quite funny how Arthur C. Clarke and O'Neill dance around one another's concepts. It's quite,
it really is, isn't it? I mean, it's quite a selfish thing, because you think that when you hear modern concepts that, of course, we've just came up with them, but you read stuff like this and you realise that it's been going on for like centuries.
50 years or so. Yeah, so 1970, O'Neill writes The Colonization of Space from his students and his work. But he then spends the next 4 years trying to get the damn thing published. And in the meantime, Arthur C. Clarke brings out Rendezvous with Rama, and Larry Niven brings out Ringworld, which have some of the concepts that are in O'Neill's work. But as we've heard, a lot of this stuff was building up anyway ever since Tsiolkovsky and people like that. It was building up. You could see that these space settlement ideas were condensing, as it were, and out of the ether itself. And then 1974, he had a 2-day conference at Princeton University called the First Conference on Space Colonization. Drexler and Dyson were both present. Tick. And it made front page news on the New York Times. So people were really into this. So this is just after the Apollo missions have all finished. And this, I suppose, seemed like it was the next big thing. And as O'Neill pointed out at the time, he said, the profound difference between this and everything else done in space is the potential of generating large amounts of new wealth.
Where was he from?
I think he was from France.
Just checking.
I don't know where was O'Neill born.
We'll find out.
1975, the L5 Society was set up. So L5 obviously named after Lagrange point. I don't know why it's not L4, and I don't really know if there is a difference between L4 and L5, by the way, in terms of its suitability.
I think we went over that when we did our Lagrange episode.
But is there a reason why the L5 Lagrange point?
Yeah, I can't remember what we said.
Is better than the L4 Lagrange point for space stations? I don't know. In June 1975, O'Neill then led a 10-week study of permanent space habitats at NASA Ames. Is available online, all the work from that, and it's really, really interesting. But at the same time,
we'll put the link up.
And you can see how serious this was all being taken by the American government. He was asked to testify to the House Subcommittee on Space Science and Applications. He then presented his case for solar power from satellites from space. You'll hear in the interview a really interesting point about that. And then he developed detailed plans to establish bases on the moon. He then leaves NASA despite getting $500,000 a year in grants to set up with his wife the Space Studies Institute, which is still going today, at Princeton University. And where he used to work more on those mass driver concepts was the sort of main sort of drive of his work at that point. So
imagine the cojones to go, I'm just going to leave NASA and set my own thing up. Love that.
Well, I think he was
legend,
bogged down with the bureaucracy of NASA at the time.
Yeah.
In 1977, he released the classic book, The High Frontier, which is well worth getting because it's got that beautiful artwork of all these Bernal spheres and and obviously O'Neill cylinders, etc., etc. So a lot of that, I think, the artwork ended up in that Bezos speech that he did.
Well, I need artwork with my books, Matt, so that will help.
Yeah, no, absolutely. You should have that book. It's interesting. He quotes space shuttle costing $10 million a launch. Really, way over 4 times that, and probably 20 times that in reality by the time you get to 2011. So the shuttle basically was a disaster when it came to what people thought it would deliver and what it actually ended up delivering. It was just too expensive. It just didn't work as planned. 1977 was the peak of this kind of interest, and O'Neill eventually was appointed by Ronald Reagan onto the National Commission on Space in 1985, and they wrote a huge piece about the government committing to opening the inner solar system for human settlement within 50 years. So
this is it.
Yeah. But that report essentially got buried because it came out 4 months after the Space Shuttle Challenger broke up on ascent. So it felt like it was lost. So there we go.
It's just mind-blowing. I absolutely love it, and I'm definitely going to be ordering a few books about this.
Oh, yeah, no, totally.
First up, The World, the Flesh, the Devil.
Oh, no,
definitely.
Absolutely. It's an easy read, that one. It's quite short, but it's so good. You just read it, and it's so well written, and it's got so many sort of interesting concepts. It doesn't feel dated at all. I mean, I'm talking about that's almost 100 years old, and it just feels...
It's incredible.
Well, it just makes you realise that people have been thinking about these things, and it goes around in these cycles of thought, and it'd be really interesting to see if someone, could really expand on those ideas in a much more credible way today. I mean, even O'Neill's work seems like no one's really taken it much further about space habitation and done, much more work. It'd be interesting to see.
Exactly.
We've seen some interesting journals for sure.
We have.
And we'll be going along some of those in the next couple of weeks when we finish off this look at habitats. But the 1975 study that he did, quite a few things came out of that, and it's quite a good one to kind of look at in terms of how does it all work? How do you design these habitats? And it kind of outlays some of the sort of important things. And one of the things that it sort of says is that you have to design a habitat to meet all the physiological requirements of a permanent population and to foster a viable social community.
It says obtain an adequate supply of raw materials and provide the capability to process them.
Mm-hmm. You've got to provide an adequate transport system to carry people, raw materials, and items of trade.
Yes, also develop commercial activity sufficient to attract capital and produce goods and services for trade with Earth.
So, for a large general population, many of whom must commute between 0G and a rotating environment, it looks like you have to minimise the rotation rate. So the only way you can get gravity is by this rotation in space. You need it, obviously, unless you're doing this on a planet. But we are talking about, these in-space habitats. But because of the Coriolis force, which we dealt with on a previous podcast.
We did.
You can see that has real consequences for messing around with your inner ear and motion sickness and things like that.
Tell me about it.
It looks like people can adapt to rates of below 3 revolutions per minute after prolonged exposure. But because they're moving in and out of these different regimes of working in zero gravity, going back to that kind of proper gravity and stuff like that, they set it for 1 revolution per minute. They think is the upper limit of a permissible rotation rate, and that then gives you a parameter that really decides the sizes of these space habitats.
That's right.
Obviously, you need an atmosphere. So what can you tell us about the atmosphere of these?
Well, human life can be safely and comfortably supported at a pressure well below that of a normal Earth atmosphere. And we've also got temperatures around 22 degrees C and a relative humidity of about 40%. And finally, the presence and various benefits of nitrogen gas dictate its inclusion in the atmosphere.
So yeah, you've got that pretty much determines what the atmosphere is going to be like, and obviously you've got to have enough water for drinking and sanitation.
A heavy workload will require about 3,000 calories a day. Should consist of 200 g of water, 400 g of dried various carbohydrates and fats, 60 to 70 grams of dried weight of proteins, and adequate quantities of various minerals and vitamins. You've got to keep your energy up, Matt.
And of course, the architecture has to be right for people to not feel isolated or claustrophobic or agoraphobic. So it has to be, there are some suitable shapes for these particular space settlements. Do you know what the 4 shapes?
Well,
basically, they were looking at colonies that would be able to sustain about 10,000 people. So what are the sort of
Well,
shapes?
We're going to have to start with spheres, aren't we? Tipping the cap to Mr. Bernal.
The rotating cylinders of O'Neill.
The torus of von Braun.
And, of course, some of the other science fiction shapes offered by Mr. Arthur C. Clarke himself.
Ledge.
To have 10,000 people, that is a living space of roughly 670,000 metres squared. And it's got to meet the psychological and physiological needs of the people, as we've said. And if you make it out of aluminium, you can start working out the kind of structural constraints. And the habitat must hold the atmosphere in place. And normally what you want is the kind of structure that holds the buildings, i.e. where the forces of gravity are acting on it. You also want that to be the structure that's keeping in the atmosphere as well. So there's you kind of have to be careful that you get that exactly right. And not only that, the shells themselves kind of have to be doubly symmetric because you're spinning them. So you have to have the membranes of a certain shape, which then sort of brings you down to those particular shapes. Basically, either a rotating sphere, a rotating cylinder, a rotating torus, or a rotating dumbbell, or sort of combinations of those kinds of shapes, composite shapes. I will put a little picture of all the different kind of things like beaded toruses and banded toruses and stuff like that. What's
really your favourite shape, Matt, out of the lot?
I think the torus. I think when you see science fiction stuff, the torus is where they end up in this particular study.
Yeah.
If you've got this rotating design with 1G at less than 1 revolution per minute, all those systems have to have a radius of rotation greater than 895 meters. So they all have to be, at least a kilometer, really.
Yeah.
But over 1.5 kilometers diameter. If you look into all the different kind of characteristics of all those different shapes, the weight of them, the radius of the sphere, how many people you can keep in them, the complicatedness of the structure, what the vistas would be like inside, all those things. Because of its good habitability properties, large volume, all the sort of possible internal arrangements and all those kind of things, and the access to zero gravity docks, the torus is the one that kind of is adopted as the basic form of a habitat. Often.
I just love it too. Those pictures that you've been putting up on Instagram have been blowing my mind. I can't stop thinking about it, of what it might be like, Matt.
One of the most famous ones in cinema recently has, of course, been Elysium, hasn't it?
Yeah.
That was a really good torus one.
Very true.
Next week, Jamie, we'll do a rundown on that paper that we were talking about, the Rama.
We will, Rama. Reconstituting asteroids into mechanical automata.
Yeah, I mean, that's pretty cool, isn't it? Do you know, the whole of that paper, they don't mention Arthur C. Clarke's Rama. It's like, it seems very, very odd. But made in space, the people that make those little plastic spanners on the International Space Station have written a very interesting article about how you actually grab asteroids and bring them back. So we'll do a rundown on that because it's really, really cool. You've got asteroids that move across the solar system like jellyfish. It's very cool.
It is super cool.
So, Jamie, do you want to listen to the interview?
I really would. Let's roll it.
Fred Scharmen, Ukute.
The Interplanetary Podcast, putting the ace back into space.
So I'm joined on the podcast with Fred Scharmen. One of our Patreons, Rob Annabelle, has kindly put us in touch with. I'm currently reading your book. Welcome to the show, Fred.
Thanks, Matt. Thank you for the invitation.
Oh, absolutely my pleasure. So first of all, can you tell us a little bit about yourself and how you've got into space habitats, etc.?
Sure. Yeah. My primary gig is teaching architecture here in Baltimore City. I'm an associate professor at Morgan State University, where I get to teach about cities and buildings. So really, also just going back for years and years, I've always been a fan of space science and science fiction. So this current book really comes out of the intersection of those two things. So when you have something like cities and architecture in space, it was a natural fit to be interested in this topic.
Oh God, yeah. I mean, it's kind of like an architect's dream, isn't it? Because you've got almost a totally new space to work with that has almost less constraints. Is that right?
It's weird. There are less constraints and there are more constraints, right? And I think, there's a lot that we could get into about that. You kind of have to, and this, thinking about it in this way kind of came through my involvement with this material as I was putting the book together. But when you're building in space, you have to design and specify everything. You can't take anything for granted. So in a sense, it's like you have to build your own constraints, which is a really unique problem. But then, as I was working with the writing, I kind of discovered that there's a lot that architects on Earth can learn from that, because we're always sort of framing the problem and building the problem and the constraints along with working within them. So in many ways, there are a lot of really continuous connections between thinking about making space in space and thinking about making space on Earth.
So tell us a little bit about the book. It's called Space Settlements, is that correct?
Yep. Yeah. The book is about the work of a physicist and engineer named Gerard O'Neill, who was at Princeton during the 60s, 70s, and 80s. And beginning with his physics students, he really started to engage in a long-term project that was the design of really, really large habitats for permanent human living in space. And so if you think of something like the International Space Station, I think it has a maximum crew of 6. And what he was interested in doing, beginning in the late 60s, was designing places for up to several million people. And right away, he decided really early on that to him, it didn't make much sense to leave Earth, and if your goal is to have access to the energy and resources in space, for him it didn't make sense to go and live permanently on the moon or go and live permanently on Mars. He wanted to advocate for the creation of basically giant free-floating cities from scratch that would rotate to create their own artificial gravity. So especially in this one specific, what NASA calls a summer study, the summer study that took place at the NASA Ames Research Center in what's now Silicon Valley in 1975, he really got a chance to put a team together and design the heck out of these things, really to create in a lot of detail specific engineering scenarios, but also specific kind of explorations of how these spaces would look and feel. So that's what the book's about, is this 1975 summer study, where for really the first time they started to get architects and designers and urban planners involved deeply in the project as well.
I noticed that there seemed to be, while reading your book, there seemed to be a slight annoyance when people asked him about, say, Arthur C. Clarke's Rama and the connection to that. Is that, have I got that right? Because as I was looking at O'Neill's cylinders almost directly after Jeff Bezos had spoke about them, obviously I'd heard about them before. I thought, well, I better do a bit more of a dive. I was thinking it's so similar to what I'd kind of read in the Rama books. So I was thinking surely they're influenced, but in your book it kind of suggests not. Is that? Tell us a little bit about that.
I think O'Neill is a really interesting figure because he's able to address all kinds of audiences. He's able to sort of speak to science fiction fans. He's able to speak to Congress. He testified before Congress about this project a couple of times. But he also gets a bit touchy because he sees himself as an engineer first and foremost. And I think in when people drew connections to his work and his work was kind of broke down into three habitat types. There was the O'Neill cylinder, which is a really big cylinder, just like it sounds. There's the Bernal sphere and the Stanford torus. So the O'Neill cylinder in particular is, of course, a really big cylinder, a lot like that rotates for artificial gravity, a lot like Rama in Arthur C. Clarke's novel. And the Stanford torus is like a small sort of ring world. It's like out of Larry Niven's series of novels, which were both out in the early 1970s. So these were things that O'Neill was exposed to. He seems to have been a science fiction fan. But in his work, especially in this great response to a letter writer in Physics Today, the journal that he first published some of this work in, who's obviously this letter writer is really enthusiastic and says, "Oh, you should also check out Rendezvous with Rama and Larry Niven's Ring World." And yeah, his tone you can read even in the text sounds a bit testy when he responds. He says these are serious proposals for actual projects, and yes, I know the work of those two writers. And he says something about neither of them really contributes to the practical application of the idea, but they came before him, at least in publication. And there are a bunch of antecedents to his work from science fiction and elsewhere. But he really, I think this is a rhetorical move on his part. He really wanted to hold the line that this is not science fiction, that this could be built. And this is another phrase that comes up in his writing a lot. It could be built with today's technology. That is the technology of 1975.
Yeah, it's funny. We had a guest on a couple of weeks ago who was talking about how some of these ideas from 1970, the sort of 70s era on space habitats, they were addressing problems that seem really naive now with some of the technology that's come along. Is there any? Have you got a really good example of that you've kind of spotted as you worked your way through the book?
Well, they take for granted that that ecosystem design could be a really easily solvable problem. And I think that's really striking because this is also an era where ecological thinking was kind of at the forefront of popular culture for really the first time in the 60s and 70s. Rachel Carson's book Silent Spring had come out in, I think, 1962, and that was read by millions. And in the early 70s, the Club of Rome's report about resources and ecosystem collapse was also in every single bookstore. As we can tell, because it's in all the thrift stores now today. But that's limits to growth, right? So it's about how the Earth's ecosystem can't support the apparent growth of human population. And this project is kind of pitched as a solution to that. But there's quite a lot of hand waving about how that's going to take place. And you mentioned Jeff Bezos's recently announced project for giant, basically O'Neill cylinders and Stanford toruses in space as his long-term plan. And there's some similar kind of dodging of the ecological questions, I think, in his work too. And Bezos was at Princeton, and he doesn't seem to have been enrolled in any of O'Neill's classes while he was there, but he did attend a lot of his lectures. And O'Neill's ideas have been really influential to Bezos, especially, and his company Blue Origin for a long time. But again, there's this question of, there's this two-sided question here. The idea that we need to make new from scratch habitats in space in order to provide a kind of backup system for the ecosystem on Earth. But if we can, there's always that lingering kind of assumption underneath that, well, hey, if we can design ecosystems in space and build them successfully, why shouldn't we apply that effort to try to do that on the planet in the ecosystem that we have now in order to get things running in a more productive way here and now as well? Which is not to say that we can't do one until we do the other, But there's this tendency from the 70s till today to just go, oh well, this is already messed up. We got to go do it again. We'll be able to do it right this time.
Yeah, well, that's always been my super objection to Interstellar, where it's like you've got a planet that's dying, and the solution is to try and find a much harder place to find where it's not.
Yeah,
it's like maybe sort out the one that works. But it's funny, isn't it? That because even Elon Musk gets trapped with that. With putting settlements on Mars as well, doesn't he? So it's a common theme, mm-hmm. Let's say. Is there any other kind of technological breakthroughs, like the flip side to that coin? Is there any other sort of technological breakthroughs that have happened in the 80s and 90s and noughties, etc., that make some of the thinking of O'Neill cylinders naive, where it's like, oh look, this solution was actually easier than we thought?
That's a good question. I think I follow a little bit some of the, in other areas of new space, some of the asteroid mining companies. And I think that there's a lot more that we know about, and I'm using we broadly here, of course, but that people know about resources that are available. Maybe a less... progress has moved slower than most people have anticipated, or than many people like O'Neill from the 1970s have anticipated. But it does seem like there's more likely to be something happening within the next 5 years in that regards than there have been in any 5-year period since, at least since the end of the space shuttle program in 2011.
Yeah, I mean, do you think that because it definitely feels as though there's been a stalling of progress on things like space stations? If you look back to, mm-hmm. again, we can mention Arthur C. Clarke's 2001 and what his mm-hmm. vision was there. It's completely wildly out. So do you think that that's down to a lack of ambition, or more to do with of an underestimating the actual problem in the first place?
Yeah, I think, and you and your listeners would certainly know quite a lot about the kind of the failure of expectations over the past 30 years in different space programs around the world. But the shuttle program was obviously much more expensive to run than anybody anticipated, and there were political reasons for something like the Apollo program to exist that don't really exist anymore. But it does seem like culturally, like ideas about the future, big ideas about the future in general, aside from economic or political concerns, are harder to come by in the 20-teens for all the technological capacity that nation states and private companies have. It's disappointing to see even the big dreams, even somebody like Jeff Bezos's 15 or 20 year plan to be a reiteration of this work from the 1970s.
I mean, there's an element of me that thinks it's the Victorians, I suppose. I don't know what you call that era in America, but the Victorian era definitely felt with the kind of engineering was how much more epic and bigger it could get with Bernal and people like this building bigger and bigger, and you. Yeah. Even Apollo felt like it was coming out of that era, but since then technology's been more about getting smaller and smaller and smaller, and I wonder if that plays a part in the fact that these things that are super epically massive just are not really the direction that technology is going in the moment.
Mm-hmm. Yeah, I think that the oil crisis and energy crisis of the early 1970s have a lot to do with that as well. If you take, and this is maybe just my bias because I've been, I've had my nose in books about and from the 70s for literally years now, but there does seem to be this seasonal, this sea change in around 72, 75. And I think if you look at energy costs, it starts to make a lot of sense because energy costs was just falling and falling and falling until the energy crisis. And since then, it's gone up and down and up and down. But that was the first sort of wake-up call that that expansionism might have an end date, which is, of course, also what the Club of Rome was saying really explicitly, that the current sort of capitalist mode of continuous expansion of GDP, continuous expansion of industrial capacity, continuous expansion of population was literally not sustainable. So in one sense, it is interesting to see that in this project from the 70s and in its ongoing cultural influence, this way out from under that. Like O'Neill will literally write and speak to Congress about how a steady state society would be un-American. So he's rebutting the ideas of the Club of Rome there, and there's a whole section of his testimony labeled "Room for Growth," which, even though he doesn't mention the book Limits to Growth, he's directly saying that this is how we can keep that line on the graph, how we can keep its motion continually up and to the right for the next century or so at least. So it is like it goes back to that Victorian era that we do need to build bigger and bigger and more. And in the real world, that line on the graph kind of started to level out or even drop. But in the scenario, that expansion of capacity in all senses was just going to keep going if we could just get out into space.
Yeah, I mean, the little we hear Bezos talking, he's been really influenced, hasn't he, by O'Neill, because he talks very much about that expansion only being possible where you flip industry into space, that you flip it upside down or whatever his particular phrase is, that industry has to be moved to space. Do you think there will? Do you believe in that particular scenario? Do you think that there is a scenario where industry, that we're kind of constrained by the environment that is Earth, and that once we are able to get industry into space, that then suddenly we'll see a lot of these epic engineering projects start again, where we've got in some ways a whole new source of energy as well, with off Earth solar power even is a hell of a lot better than it is down here. So do you see something like that happening?
There are a couple of things. There are a couple of things that brings to mind. One is that I actually just went on a tour of an Amazon fulfillment center yesterday here in Baltimore, and the sheer, I mean, when you're in one of those buildings, I don't know if you've ever been in one, but if you have, I'll tell all your listeners that if you have the chance to go on one of these tours, they're free tours. You book them in advance. I don't know if they do it the same system in the UK, but go on the tour because you're in a giant machine. I mean, there's all kinds of impressions that take away that I'm still processing about that tour. But the overall sense that you have is that you're inside this giant mechanism. So after that tour, I think I'm completely convinced that if anybody has the capacity to mobilize all the supply chain, right, that would be necessary for a project like this, that it would be Bezos. The other side of that is that there are all kinds of externalities sort of waiting in the wings that nobody's really figured out yet. You mentioned Bezos mentions putting an industrial base in space. Energy from space was certainly part of O'Neill's project. The people living in these habitats were going to be building giant solar satellites that would beam down power via microwave to ground-based receivers. And O'Neill tells Congress that this is going to, quote, put the Middle East out of business. So it is again, it's about the oil crisis. There are all kinds of unknowns in that scenario. I mean, I've spoken with physicists who say, well, just in terms of the inadvertent heating of the atmosphere in the path of transmission from a space-based sender and an Earth-based receiver, that would add more thermal energy, more BTUs to the planetary environment. So there's no, and to the tune of somebody, it was a friend of mine on Twitter that did back of envelope calculations, but to the tune of about 2 degrees Celsius per century. So there's no, energy is really tough, right? Because energy, any use of energy is by definition exothermic. You're going to be producing heat because there's no efficient transition from potential energy to applied energy. So the waste is heat. Even if we're not burning fossil fuels, we're going to be heating the atmosphere and the biosphere anyway. and again, even in the 1970s, physicists were concerned about what they called I can't remember the actual phrase, something like peak heat, but just even before global warming was really on a lot of people's radars as a side effect of fossil fuel consumption, physicists were talking about how just the application of useful work creates waste heat, and even to the point where Sebastian von Horner, I think is his name, who was a SETI scientist, to search for extraterrestrial intelligence. In the 1960s, he was publishing papers saying, look, any civilization as we know it is going to produce a bunch of waste heat, so we should just go look for the waste heat. We should look for any planetary or solar system body that is just radiating way too much in the thermal end of the spectrum than it should be. And that's where we'll find civilizations, because we were doing it too. And so there's no, and again, of course, a microwave, an orbiting microwave is also like kind of a death ray too. So whoever controls that kind of system is going to throw the balance of global or solar system, whatever you want to call it, power off its axis one way or another. And so there are political externalities, there are externalities just in terms of thermodynamics and physics that are really hard to get around. I mean, the laws of thermodynamics are really hard to get around, and getting off the planet into space. Even if you set aside, right, we were at a fulfillment center, even if you set aside the question of fulfillment, I mean, what are they going to do? They're going to airdrop an iPhone from orbit? If I order this is my Amazon Prime delivery. They'll manufacture it in a space-based facility, and then you still have to get it down to the planet itself, which involves a whole kind of set of other questions too. Not the least of which are the thermodynamics involved there too. Getting a bunch of stuff down to the planet is going to create a lot of waste heat as well too. So I think there are a lot of unknowns in all of these problems, just like there always are with any large engineering project. But it's disappointing to see them glossed over even today.
Yeah, I mean, I guess anything that's epic or on a sort of world scale always has unintended consequences. You never know what those are going to be. Even if it's Twitter, always has unintended consequences.
Yeah.
So it's very, very hard, isn't it? And I don't think any science fiction writer has ever really tackled it with great gusto. I mean, I know that they've tried, but it's you always the assumption is that somehow those things have been solved rather than a still ongoing massive problem all the time.
And a lot of things have gotten solved. You know, people will always answer that criticism with quotes from the early 20th century about how rocketry will never be technically feasible, or how no one would ever have any use for a computer outside of 4 or 5 global companies, things like that. So but it's worth having the conversation either way.
Oh yeah, absolutely. I mean, what's always funny is how people miss the technologies that do become world changing. It's quite funny reading science fiction, Star Trek, where they haven't even thought about having a mobile phone in your hand with the world's knowledge on it, with a screen. It's just, and that's just run of the mill. We don't even think about it technology these days. So with back to O'Neill cylinders, do you think that O'Neill cylinders have a kind of? Do you think that they do have a future? Do you think that is something that where we're going to go or have they been surpassed by other technologies or other ideas, do you think?
I think architecturally, spatially, there's a lot of really fascinating things about the kind of solution to the problem that O'Neill and his collaborators hit on, which I think the key insight is you make a ground, instead of having room and room and room, like say the space station in 2001, where you have the space hotel or whatever, you create a whole new ground, and then you build structures on that ground that are kind of independent of the ground. And that Stuart Brand and others writing in the 90s, actually his source was the president of REBA at the time, the person he sources this idea to. in a book called How Buildings Learn, which is about basically, it sounds boring, but it's about building renovation and how people renovate and update existing buildings in cities. He writes about how the structure changes much more slowly than the stuff inside, and then there are a whole bunch of layers in between that. So, we might move our furniture around more often than we punch holes in the wall or arrange the partitions, that define a room. And even more rarely than that do we do structural work. Even more rarely than that do we do landscape or foundation work that really affects where the structure meets the ground. So the independence of those layers, Stuart Brand was finding that built in implicitly to the way we use architecture in cities. So O'Neill independently kind of applied that idea that the ground itself would be independent from the structures on top of it so that the flexibility could be maintained. And, of course, it's much more comfortable to feel like you're living in a big open space that you can see and understand than it would be to live in a series of small capsules like in a submarine or in, say, the International Space Station today.
Yeah, is there any kind of real downside to getting essentially your fake gravity instead of from a massive body, you're getting it from a rotating body? What's the kind of downsides to that? Because presumably they're not identical.
Yeah. There was a physiologist on the team at a few of these meetings in the 70s named Ashton Graybeal, and he had done work going back to the 50s and 60s with the Navy and with NASA that involved large rotating rooms, and they'd spin these Navy guys around basically until they puked, and then compile the statistics about what spin rate makes the most people puke and what spin rate makes fewer people puke, and what are the safest and most reliable sort of revolutions per minute that humans can take. And I found that about 1 RPM, you could pretty much guarantee nobody's going to get ill, because basically the problem is if you move your head in different directions, the force vectors are doing different things to your inner ear. So your sensation of down gets subtly thrown off in terms of the body's sort of fluid system. It's now no longer in alignment with what your eyes are telling you is down. And that's that sort of that's seasickness basically. It's the same mechanism. So that RPM sets the size, because if you have a larger object and you want to create one gravity, one Earth gravity inside it, you can spin it more slowly than a smaller one. Small radius means you have to spin really fast, which means more people are going to puke. So the size of these things is a consequence of the sort of physics and the physiology, which is really interesting too. In practical terms, again in 2001, a certain percentage of that Space Hilton's customers would not be happy in that environment because it's a relatively small radius. You need about a half mile radius in order to get 1 RPM and generate 1 gravity, which is a really large habitat. That's what sets the size of the Stanford Torus and the Bernal Sphere, which were supposed to have a population of about 10,000 people.
Yeah, but it kind of works out quite neatly, doesn't it? It feels like that's a sort of doable size. So yeah, that must have when the calculation all fell out, they must have all patted each other on the back for that one.
Yeah.
Is there any other constraints like that, or does it seem that it is just the rate that you're rotating?
Another thing that we, again, people who follow space science, know a lot more about now is radiation, and that's a really tough problem to solve too. That was sort of a little bit hand waved in some of the proposals that I studied from the 70s, because that's going to cause its own kind of physiological problems, of course, too. And then also the question of moving more or less, at regular rates back and forth between zero gravity, where you do industrial work, where you'd have that industrial base, because that's one of the benefits of zero gravity is that it's much easier to assemble large things, and you can do it with free energy from the sun, etc. but you'd be going back and forth, right? You'd be sort of clocking in at 0G and then clocking out and then going home at 1G. And then you do it again the next day or the next week, however the shift worked out. And that's a really understudied problem physiologically too, because we tend to keep people out in space. If we're going to take the trouble to send them, we want them to be there for a little while. We're not going to just sort of take them up and take them down again. But if you're in one of these habitats, that's the benefit, is that you can easily go back and forth. But there probably will be, the physiologists said, problems that could arise from that back and forth between 0G and 1G too.
Yeah, but presumably there's, if you have a building on the ground, as you go up the stories, your gravity significantly drops more than it does on a massive object. Does that have does that actually have some engineering problems associated with it?
Probably it's a benefit, because you can build taller and taller and taller already, and many buildings use this expressively already. Of course, with every new story, it's going to be carrying less weight, so you can make the structure thinner. Even on Earth, that's the case, and people use that architecturally, spatially. I think another interesting question that gives rise to is the notion of a kind of social hierarchy built into the architecture too, because even on Earth, in our cities, to go higher is to gain access to more, what urban planners constantly talk about in terms of light and air, which are rare resources in cities. So there tends to these layers tend to map to class. Even the kind of image of the CEO or the tycoon in the penthouse is a really familiar one. So if that privileged position also maps to a literal sort of lighter weight, what does that do in terms of how cities and buildings inside these habitats would be? What does it do to how they'd be constructed socially and architecturally, and how that architecture would relate to or map to culture and class?
Yeah, but I wonder if it would get to the point where you'd make some of the lower floors even more than 1G, so you kind of breeding in a working class that are stronger, I suppose.
In science fiction, that the lower levels are always where where the workers are, and where there's the talk of revolution, whispered among the pipes, and then the upper levels are where the kind of blasé, clueless, usually in the imagery, white, blonde, Nordic peoples are going about their business and exploiting the people below. So this is an old scenario in science fiction, and it's one of the ways in which science fiction functions to kind of warn us about unintended cultural and political consequences of the way we think about the future. And this is going to show up in these scenarios that people were talking about here too.
Yeah, it's super interesting, the psychological and the social aspects of it. What was the most exciting and most revelatory thing that you discovered while writing the book and delving into all these materials?
I'm fascinated by the opportunities to really work against all those limitations. If you can build a space from scratch, and this is something that I write about in the book a little bit, even architectural space on Earth is always going to be implicitly sort of for certain people and not for other people. For instance, I live in a 200-year-old house. It doesn't have an elevator. A person who's using a wheelchair would not be able to buy this house without spending a lot of money to retrofit it or change it. The way we construct space, we're always implicitly constructing a type of person who the space is for. So I think there are, and that's here when that's tied to not just, say, the light levels, the temperature and humidity of the air, when you can also design the gravity, when you can also design the ground, there are constraints there, but there are also opportunities to redefine who those things are for. I think there is the chance, and this is utopia and dystopia always haunts these future scenarios, and there is a chance to sort of to think about applied utopian thinking to really make space that was for as many people as possible. And then also, related to that, there are other things if we're putting together whole societies in space where certain resources are really abundant and certain resources are really constrained. I think there's the opportunity, and this is to really not just create the architectural space in a way that is as inclusive as possible, but to build new models of sort of access to basic human needs that could also be as inclusive as possible. For instance, right now, the Outer Space Treaty that was ratified in the 1960s by a bunch of the countries that had spaceflight capacity at the time. There's a provision there for right of rescue and return, which is part of the responsibilities of any astronaut, any space-going human, that if you encounter another space-going human who is in trouble or in need of assistance, you have the responsibility to rescue them and offer aid. Right? It's sort of based on laws of the sea and things like that. But that's a really utopian. It's a really utopian sort of political concept too, about rights to resources. If this is sort of similar to the idea that if we could design an ecosystem in space, why can't we intervene in the design of ecosystems on Earth that are breaking down? If we can create a kind of utopian political situation where there is this basic principle of mutual aid and mutual access to the necessities for life, food, air, water, why can't we map that back down to Earth as well? So there is I love that thinking about the future and thinking about these distant spaces and thinking about the potential capacity to create whole worlds architecturally, politically, economically. It also offers us a lot of opportunities to say we can do that. We can do that anywhere. We can do that on Earth. We could offer guaranteed access to basic human needs and human rights here, just like we could maybe intervene and fix the ecosystem here if we consciously try to develop these capacities.
A hard nut to crack, isn't it? That trying to come up with problems in science and solving them with technology, engineering, science, etc., rather than just letting the scientists get on and discover things and then roll that back into changing society. It's good. It's good that there's both those mechanisms, and you're absolutely right that thinking forward can sometimes pay off. I mean, you only have to look at the Apollo, I suppose, mission has fed back into society in a very positive and not really foreseen way when they were doing some of the things that they were doing. I guess the famous architectural one is the vibration shock that's built into a lot of buildings to resist earthquakes from the Apollo launch towers and things. So but it wasn't explicitly designed to stop earthquake damage, but it's just sort of found its way there. It's a kind of advocacy for just letting engineers get on with what they do best and just solve problems of their own and hope that it pays back, I suppose.
Yeah, and often that stuff, if that model of like basic research is the base, then often any products of that basic research just end up recuperated to reinforce existing political or economic norms.
Where can people read about what you're up to, or get your book, or learn more about some of the stuff that you've been doing?
Sure. I don't have a sort of a writing website or anything. I probably should put that together, but the book is available from Columbia University Press. So from their site is one place to get it. Or if you want to, I would say if you want to help fund Jeff Bezos's ambitions by giving him a little money too, of course you can get it on Amazon. You can find me on Twitter most of the time. I'm at 765 on Twitter, and I think there's that sort of the way Twitter exists almost as a utopian place where you can just sort of start conversations with physicists and ask them questions, start conversations with people in space science, or my favorite new field is science and technology studies. And I made friends with a lot of anthropologists on Twitter. I love the kind of the utopia of Twitter and the way it makes communities out of different types of people, again, that you wouldn't ordinarily expect to encounter in spaces that are overly constrained.
Yep.
So yeah, at 765 on Twitter.
Fantastic. Yeah, it's both utopian and dystopian, isn't it, Twitter?
Exactly.
Thank you very much for coming on and talking to us. Is there anything about space settlements that you'd like to say before I say cheerio?
Oh, just that somebody's going to do it sooner or later.
Yeah.
Right.
What sort of time frame? What sort of time frame do you put on it?
Oh, that's dangerous.
Yeah, but I demand an answer.
Let's say, yeah. I mean, I wouldn't be surprised if let's say this. I wouldn't be surprised that the International Space Station has been continuously occupied since the early 2000s or late 1990s. Mm. I wouldn't be surprised if we're already in the era of humans permanently living in space.
Yeah.
Let's say that there will be humans in space from the initial occupation of the ISS onto an indefinite future.
I almost feel like you've copped out there. What I really want is the one where a something like the ISS that's a permanent, where you could actually say, yeah, that is a self-sustaining permanent habitation.
I'll make a hard prediction then. So in the back of NASA's official report from the 1975 summer study, they have cost estimates, and they costed out the Stanford Torus at, I don't remember the 1975 figure, but I had converted it to 2018 dollars. It was $850 billion in 2018 dollars, which is honestly not that much.
No,
the global financial bailout was like 3 times that. So I'd say that a construction of, say, a rotating permanent human habitat in space will probably be underway within by 2040, 20 years.
No way. Okay, that's a good one. That 880 billion, of course, if we treat it in the same way the James Webb Telescope
exactly.
price rose,
yeah,
it starts off as a good figure. It gets frighteningly larger, I would think.
It only goes up from there.
Yeah. Notoriously bad at getting that right. Thanks very much for having the conversation. It's been absolutely brilliant.
Thanks a lot. That was really enjoyable, man.
The Interplanetary Podcast is alive!
So there you go, Jamie.
That was ace.
A little bit of a history lesson on O'Neill and some social stuff as well. He was a really, really cool guy. I'd love to get him on again.
Really cool guy. Yeah, let's hope he's a regular. Super cool stuff.
Yeah, super cool. Thanks very much to Rob on the Discord for hooking that up. In fact, really coming up with a whole idea of all of this stuff.
Yeah, cheers, Rob. And Matt, if you want to join the elite Discord crew, what have you got to do?
Just gotta get yourself over to interplanetary.org.uk. Have a little wander around there, click on the Patreon button and maybe join up. And if you become a patron, you automatically come over to the Discord channel and you can join in the conversation and shape future shows just like our Discord crew always do. They're legends.
Which shape will you choose?
Plum shape.
Oh, don't start that again.
That's not the plums again. Jamie, did you know?
Yes.
If the Earth was the size of a pea, Pluto would be a small grain of sand about 2 miles away.
I didn't know that, but I like it.
I like it. Imagine a pea in the Royal Institute, sitting on like a tiny plinth in the Royal Institute, and that was the Earth. And then you walked all the way across London to Temple Tube Station, say, and then saw on the floor a piece of sand, a tiny grain of sand. That's the equivalent scale to Earth and Pluto. It's just insane.
It is ridiculous.
It's just
and to have the audacity to not call it a planet. I mean, get out of here.
It makes you realise how empty the solar system is, though, doesn't it?
Really is.
That's why mining asteroids is really, really difficult.
It's the future.
It is the future.
And I'm going to be one of the pioneers. You heard it here first.
Yeah, it's goddamn difficult. Anyway, Jamie, you've got to go, haven't you? I've got to go,
but I wish everybody a good weekend. And, you know, I'm going to bury this podcast for 50 years in case we get humiliated.
That's exactly what I was going to do as well. Or if you were listening to it, we decided against that.
We decided against it. Well, have a good weekend, everyone. Goodbye.
Bye-bye, Spodcats. Au revoir.
See you.